For those of you who do not know me, I'm Tim White. I'm a research professor in the Earth and Environmental Systems Institute at the Pennsylvania State University. I'm a field geologist, and I spent the last roughly 12 or so years working with the U.S. Critical Zone Observatory program, which is now defunct and has been replaced by another program. And I'm the PI on the ABRESO project. So my aim today is, for now, is to provide you with an introduction to this workshop. You can see the agenda for today is in front of you. I'm going to give you a brief introduction to the project, and then I'll be followed by lightning talks from each of our working groups. And then at about 7:30, we'll shift over to 30-minute presentations from our Japanese and US colleagues. Oops, let's see what we got here. Why am I not? There we go. This is the first of 3 days of workshop. And so the next meeting, also for an hour and a half, will be on November 14th. At that time, we'll have 30-minute presentations from each of the remaining national partners, France, Italy, and Taiwan. And then day 3 is set aside specifically to discuss integration and integrative activities across the project. So we'll have a brief presentation from Osamu and Janet, and then that will be followed by breakout discussions. So I was part of an international team of natural and social scientists who met in Vienna in 2020 to help promote and guide the Belmont Forum to develop a program based on the concept of the critical zone. And though in the end, the term critical zone was not included in the title of the call, you can see that it is stated prominently there, highlighted in yellow, in the description of the call for proposals. And for that reason, I'm just going to spend a brief amount of time describing and reminding for some of you what the critical zone is, because you may not be familiar with it. And I'll just remind you that this call for proposals is what's supporting our ABRESO project. So the term critical zone was first published in 1999 in a Geological Society of America abstract by Gail Ashley, a geologist at Rutgers University, and then more formally in a U.S. National Research Council report, Basic Research in Earth Science, Basic Research Opportunities in the Earth Sciences in 2001. And the term defines the thin veneer at Earth's surface spanning from the top of the vegetation canopy, whatever that might be, through soil and sediment and bedrock down to the base of the fresh groundwater zone. It's the zone that people like to call where rock meets life, and most terrestrial life exists and depends on. The upper boundary of the critical zone, as I said, extends to the top of the vegetation canopy. It's easy to see because we live in it, but it is heterogeneous and complex, and it often requires high frequency information to fully understand. The lower boundary generally equates to the base of the fresh groundwater zone, and that's a fairly diffuse boundary of variable depth depending where you are on the planet. It can be up to 1 kilometer below the surface. It's more difficult to define than that upper boundary, though the relative paucity of life and lack of the atmosphere somewhat simplifies its study, and therefore can, in general, you require lower frequency information to understand. Critical zone science aims to understand how those various realms of the zone, rock, soil, life, water, air, and organisms, influence Earth. And the science has evolved from the recognition that various diverse groups of Earth surface and environmental scientists were asking questions similarly, but they didn't typically collaborate. And so the CZ Science has brought together a relatively diverse and disparate community of scientists to build alliances to answer societally relevant transdisciplinary questions, like what processes control fluxes of carbon, particulates, and reactive gases over different timescales? How do biogeochemical processes govern long-term sustainability of water and soil resources, something that's very near and dear to this project? How do processes that nourish ecosystems change over human and geologic timescales? And how do variations and perturbations to chemical and physical weathering processes impact the critical zone? So the science is society relevant, and in particular, when we think of ongoing climate and land uses changes to the critical zone, they may stress terrestrial life, including us humans. So a better understanding of critical zone processes and function may aid adaptation to change. And this project, our ABRESO project, builds from critical zone science to help understand humanity's relationship to the critical zone. So our project, the full title shown there, Abandonment and Rebound, Societal Views of Landscape and Land Use Change and Their Impacts on Water and Soils. And the overarching goal of our project is to develop a global transdisciplinary platform for understanding the impacts of land abandonment on the sustainability of soil and water resources. On the map on the left, you can see that our project consists of partners in Taiwan, Japan, France, Italy, and the US. And it spans a wide range of physical and social environments. So for example, Taiwan and Japan are very tectonically active landscapes, as witnessed by the recent earthquake this fall in the southeast of Taiwan, whereas in the eastern US, especially, less so though in France and Italy, the landscapes are more passive geologically. And further, while the various land uses and types of abandonment vary, they all involve the cessation of historical human use of the land, some involving a new human use, while others have abandoned the land to nature. The plot on the upper right shows mean annual precipitation plotted versus temperature for our study sites and demonstrates the wide range of climate of our study landscapes. The plot also shows the wide range in bedrock types and the state of forestation across our sites. And finally, the plot on the bottom right, you can see one measure of the effects of a society's culture on the values of the citizenry and how these values may relate to behavior. For example, showing that the Taiwanese culture aims more towards a long-term collectivist approach, whereas in the US, our culture is more individualistic and short-term, with other partner nations lying in between those two end members. So one of our main goals is to understand how these varying attitudes may relate to understanding critical zone science and how that might be applied to land use decision-making and planning. Our project considers that changing climate, demographics, and human needs and perceptions are all potential drivers of land abandonment. And we meld the natural and social sciences to address the evolution of soil and water resources in response to these drivers. We use advanced techniques to understand how biophysical and societal landscapes are linked to water and soil resources and decision-making, and extensive collaboration with stakeholders has already occurred. Just as a reminder, we are organized as shown in this slide. Overall leadership and oversight is through our US team, but all project governance and decision-making are accomplished at this level through our management committee, consisting of representatives from the social and natural sciences from each partner nation. The overall project includes all the PIs and their teams of researchers, staff, students, and stakeholders, And each partner nation has its own approach to managing their in-country activities. We have also established working groups that meet on an ad hoc basis to progress various primary aims of the project. And you'll hear more about those as soon as I'm done talking. The goals of the project are, and these here are just listing the research questions that we stated in the proposal, are to answer questions like, what are the environmental, economic, and social drivers of land use change? What underlying mechanisms explain the spatial and temporal patterns in environmental quality of soil and water that are altered by different land management patterns? Does understanding stakeholders and their perceptions of land use change help explain and facilitate the development of sustainable land management? And finally, what are the possible future pathways of critical zone structure and function and their impacts on humans and nature under different scenarios of landscape and watershed management? Thus, in addition to the natural science approaches, we assess stakeholder perceptions of the drivers of land use change, land use and its consequences tied to natural science assessments, past and forecasted land use policies. And we test predictors of perceptions based upon attachment to place and how people value nature, and formulate policy recommendations as constructed or prioritized by stakeholders. Now, since my presentation is really limited in time, I'd like to discuss a couple opportunities that you have to engage in the project. First, most of you should be aware that we've held 2 virtual workshops last year. The agenda for the first one is shown here. It was designed primarily to be informative and provide the wide range of participants in the project to get to know each other and begin to discuss collaborations. And in that first workshop, we had breakout discussions focused on the major research questions that I just read to you a slide or two ago. Then the second workshop was organized specifically to address comments that were made by all of you after the first workshop. And the comments basically said that we didn't have enough time to have discussions. And so the second workshop was meant to provide more opportunity to have discussions between the various national partners and collaborators, and also to progress and evolve our overall ABRESO collaboration by focusing on what we intend to accomplish together. And I think most of our view, we accomplished the first goal, not so much the second. And today, or at least over the next 3 days of this workshop, our goal is to really come together and think about what we intend to accomplish together. Other things to consider, some of which we'll do over the next few days, is the Belmont Forum. The original call for proposals led to our funding requires that we have funding set aside for 2 people from each country to participate in an annual meeting. And last year that was done virtually through the Sustainability Research and Innovation Congress. This year, the Belmont Forum Secretariat has mandated that we participate in the SRI meeting that will be held in Panama this year. And there will be virtual attendance options, but one of the things we want to talk about is how we might present our project in that meeting. And here's an example of the kind of thing we might do. This was a workshop we held at American Geophysical Union meeting. You can see it was focused on influencing the Belmont Forum to create the CRA, the collaborative research action that they ended up creating and ended up funding this project. So we'd really like to build a workshop that will allow us to progress our ABRESO project, but also help build a future framework for continuing successful international collaborations. If you're not aware, we established a website on the czen.org existing website, and Bernd Haupt will talk briefly about that in a moment. We have We have established an international scholarships award program for graduate students and postdocs. This builds from a similar program that the National Science Foundation in the US funded. And you can see for our project this year, we supported 11 graduate students and postdocs efforts to go to different field sites or labs. Some of them were your students, some of you hosted some of the students, and we'll offer these again this year. So please make sure your teams are listening for that opportunity. Finally, we have funds to support a summer field school similar to one that we ran earlier. And our funds can support faculty, lecturers, and graduate students and postdocs. And so this is another one of the topics we'll discuss in day 3 about how we might want to pull that together. So I'm going to close there. I realize that was a lot of information in a short period of time. If anybody has any questions, because I don't have time to take questions right now, there's my email address. If you don't have it, feel free to reach out to me at any time.
Thanks. So my name is Bernd Haupt. I work in the same institute as Tim. And I'm giving you about a short overview about the web presence that we set up a while ago. So Tim mentioned already that ABRESO is part of the overarching CZO or critical zone network. There are in total 6 projects in this proposal, and I'm just talking about ABRESO here. Tim, can you go to the next slide? So this is our website. We set this up. What we did is we split it up into different sections. We're on our landing page. And one of the previous workshops, one request was to make this website more vibrant. And before I go into that, I would like to point out that we wanted a website that's fully ADA compliant. That means Americans with disabilities. So for us, it's important that everyone who's can use the site regardless of the physical status. What else is important? We are fully device agnostic. We started out with a web page that was more like designed for a PC, but now we have all these phones, tablets, and so on. So it works regardless where you are. And the facelift is that we added for each of the participating nations a flip card. Tim, can you start playing the video? It's under the right panel. There's like a little play button. Yep, go up a little bit. Go up, go up, go up. I see your mouse. And then there, hit the play button. So, all right. So for each of the participating nations, we have a flip card. Rather than going to the menu, when you hover over it, this right now is very quick. You get a very brief overview, and then you can go from there to each nation. Let's see, I'm doing it as an example for the overview page. Let's see if that's coming up. Yeah, there it is. So instead of going to the menu, and then you get like more information about the main project, the main ideas, but also each nation. Can you go to the next slide, please? Tim, can you advance? Yeah, there we go. So what we have done is we sorted out our information by nation. That's like the overview. We have a people page where we list, and I'll come to that in a minute, every person who's involved in it, but also our publications, they're all listed alphabetically by nation. The other information we have about the content, the science behind it, we are listing by work groups, as you can see on the right panel here. So in addition to that, we have on those pages like a quick overview, and in future we will add more content to it as it comes in, as like information is being published. So but what we have for that, each nation and each person that's involved in it is listed on the right side with information. So if anyone in the world has questions, they can directly go to this person and address them. Can you go to the next slide, please, Tim? So this is our people page, and I just mentioned that we list all our participants, we give credits to them. So all our team members are listed here. In addition, we list our sponsors. There's one for each nation. And so if you want to learn more about the people who are involved, and I put Tim on the spot here since he is the PI, so you see on the right panel, there are all the little buttons from each of the people who are there. And if you click on one of them, you get more information about them, as you see on the bottom right panel. So there's like an email address where they reside. We have like their research interest there. So if you have a specific question about the project, you can find out who is doing what. Tim, can you go to the next slide? All right. So we also want to have like a kind of a history of our activities, but also what's coming up. So since we are part of the CZAN Critical Zone Exploration Network, so we link back to the website to CZAN, but our focus here is we want to stay what ABRESO does. So we give on the left panel here like an outlook, what meetings are coming up. The second from the top, you can see it, that's right now our ABRESO workshop. But we also wanted to preserve the history, what has been done. And you see this at the bottom of the left panel, it says past events, and then go to the center one. You see that that's like an example. That was a workshop held recently.
All right, Adam, how about it?
All right, thanks, Tim. Hi, everybody. I'm Adam Wymore, and I'm at the University of New Hampshire and leading the concentration discharge working group. Concentration discharge relationships are a great way to understand critical zone structure and function, and some of the controls on water quality and surface water chemistry. Next, please. I'm just going to briefly go over two projects that we've been working on. One that looks at the foundation of CQ analyses, and second one to look at the role of hydrology to impact carbon and nitrogen relationships. Next, please. This is a figure just very briefly showing the publication history of papers examining concentration discharge relationships. And you can see since about 1970, there's been a steady increase, if not exponential increase, in the number of publications on this topic. But I want you to notice in the beginning, two papers in 1970 and 1971 by Francis Hall. Next, please. You'll see in the small panel on the bottom left is a figure from Francis Hall's paper that has 6 data points in it. The panel on the upper right, which is exactly the same axes, has about 44,000 data points in it. And this really reflects the changes in the data that we're able to use to study concentration discharge relationships. Next, please. So these two papers by Francis Hall are highlighted here. They came out in Water Resources Research. And these papers are important because they set the foundation for the equations that we use to understand these CQ relationships. But what I want you to know about these very important papers is that Francis Hall developed these equations using 34 data points. One of our first projects is to re-examine and really rigorously test the assumptions and equations that we use to determine CQ relationships. Next, please. The figure on the left, or the table on the left, are 8 equations that were developed by Francis Hall to evaluate CQ relationships. You can see that they get increasingly complex very quickly. But the top one is what we call the power law relationship. And this is the most simple relationship, and the one that we use and have always used to evaluate these CQ relationships. But again, this has not been rigorously tested, especially given the increased computational power that we have and the new data sets that we have, especially high frequency data sets. The figure on the right is just a brief summary of some of our results that show show the results in terms of how these different equations perform to predict CQ relationships. And we've done these at different time steps and evaluating different methods. Without getting into details of these analyses, we actually confirm the results here of Francis Hall using high frequency sensor data, and that the power law is still the most parsimonious model to evaluate CQ relationships. Next, please. I'm going to just briefly switch here to our second project, which is examining the role of hydrology to impact carbon-nitrogen relationships. What you're seeing here are two different ways to evaluate carbon-nitrogen relationships. In the one on the left are relationships between nitrate on the y-axis and dissolved organic carbon on the x-axis. And on the figure on the right are dissolved organic nitrogen on the y-axis and dissolved organic carbon on the x-axis. You'll see that these relationships are really variable. These are sites from our New Hampshire study watershed, especially the nitrate DOC relationships. You can see take a lot of different forms. So what we're doing is we're evaluating the various climatic and hydrological and land use controls on these different relationships so we can understand how nitrogen and carbon is moving together. Both elements have very important implications for water quality. Next, please. These are data from our partner sites in Taiwan. And you can see just this shows a nice example of how we can work at different scales, which is really a fundamental part of this project. We have DOC nitrate relationships on the left side at the regional scale. And you can see there's a nice linear relationship. But if you look at the site-specific scale on the right side, you can see that relationships are highly variable, including more flat relationships and negative relationships. So understanding these patterns at scale, which our project is uniquely designed to do, is a unique opportunity that we have. Next slide, please. And here, just briefly, we're showing some of the relationships of river discharge and controlling these relationships. You can see DOC, DON, carbon-nitrogen relationships on the left, and DOC nitrate relationships on the right, colored by land use. So this is just an example of, you can see the amount of data that we're able to use and some of the different analyses that we're applying in both of these projects. And again, this is now using the power law, which we verified originally from the Francis Hall papers. I think that's it, Tim. Oh, we got one more. Similar types of data here, but now we're looking at seasonal variation, including both in classic kind of 4-season type of application on the left, autumn, spring, summer, winter, but also by wet and dry seasons, which really characterize the climate in Taiwan. So just some examples of different ways that we're exploring these data to understand the controls on surface water chemistry. Okay, now I think that's the last one. Thanks, Tim.
Thank you. Hi.
The lead social scientists in each country have worked together to create an identical survey that will be given within each of the countries. Here's a pictorial representation of the areas within each country where we are collecting our data. We are aiming for 300 residents per region. Data will be collected online or in person, depending upon the feasibility within each country. Here are our 4 primary research questions. First, how do residents think land has and will change in their region? Second, what land use preferences do people have for abandoned lands? For example, do they want to keep the land the same or have it changed to a different type of land use? Third, what types of impacts do they perceive land use has on the critical zone? Fourth, do the answer to the above questions vary by country context and characteristics of the respondents? We constructed a complete version of the survey that was distributed to a sample of 300 residents in the US with proportional representation by states. This allowed us to test the length of the survey and whether the survey questions would address the questions we established. Researchers from each of the other countries has gathered data from a relatively small group of people, about 30 residents per country, to test whether there's any region or language-specific considerations that we need to address. The survey begins by defining 4 types of land use: wild forests and grasslands, productive forests, farmland, and built-up plan. We needed to restrict the number of types of land use to keep the survey to a reasonable length. The selection of the 4 types of land use were based upon predominant patterns across each country. There were 3 sections of the survey that addressed the first 3 research questions. For the first research question, how do residents think land has and will change? Respondents indicate the proportion of each of the 4 types of land could be found in the region and how much they thought it had changed in the past and will change in the future. For the second research question, what land use preferences do people have for abandoned lands? They considered each type of land use one at a time. They were to imagine that a particular type of land use was abandoned. Then they indicated their preference for how that type of land would be used. For example, they were told to imagine that a farm had been abandoned. Then they were asked how strongly they preferred the abandoned land should stay a farm, be converted to wild forest, develop into a productive forest, and be built up. For the third research question, what types of impacts do they perceive land use has on the critical zone? They indicated how each type of land use would impact different elements of the critical zone, ranging from the air to the bedrock. For our fourth research question, we will look at whether the answers to each of the questions differ by country and characteristics of the people who responded. That includes how they value nature, their attachment to the region, how concerned they are about the state of each of the elements of the critical zone. Here's an example of some data we collected in our pilot survey. The types of land described as being abandoned are shown with the 4 colors as labeled in the legend. For example, the blue color represents people considering the abandonment of wild forest and grassland. What they want done with the land is represented in the 4 clusters for each of the types of abandoned land. The numbers range from 0 to 4. If they said 0, they didn't have a preference for that type of land. If they said 4, they strongly preferred it. In the US sample, there's a preference for more natural states, as can be seen by the larger bars to the left and the smaller ones to the right. However, there's also a trend to prefer the land remain as it was. This status quo preference are illustrated by the bars with stripes. We will look for systematic variation in preferences. Here's an example of how the preferences could differ by country. For example, if you look at the striped yellow bar for Taiwan versus the other countries, there's a more predominant tendency to keep built abandoned land as built land. Please note, however, this is not our final data sets. They are from our pilots. We have updated questions based upon the pilots, and we will collect more data specifically in the study site regions with larger samples. In the next 3 months, we will launch our final survey in each of the 5 countries.
And by the way, that was Janet Swim from Penn State. Thanks, Janet.
So folks, I wanted to give you all an update on the Hydrologic Models Working Group, which has really only begun to get kicked off. And Sandra Lanini and I have been pushing this forward a bit, and we will be reaching out to others who had expressed some interest earlier in the process. Next slide. And so what we'd like to do is to use the stream discharge. We've heard about stream discharge controlling chemistry at our sites, and we'd like to use stream discharge as the response variable to understand how water availability, and especially the base flow, so the amount of water available at low flow, how that's related to the critical zone broadly. So what does that mean? The first thing we'll do is to look at long-term records of stream flow, average daily flow, perhaps the same as watersheds used in the CQ analysis, but we would expect to include others. Dr. Lanini will be assessing the R code that's available to determine base flow index, other hydrologic parameters. And if her experience with French sites is successful, we'll then apply the method to sites with different land use trajectory to look at changes in base flow index, or other parameters of base flow as a function of changes in vegetation dynamics or climate over time. Next slide. And so the proposed timeline is a meeting in early to mid-January of 2023, so in a few months, to get people up to speed on what we might do, assessment of the R code by Dr. Lanini in January, February, and the plan for how to move forward in sometime in spring of 2023. So this is a new initiative that had been discussed briefly in past workshops. If you'd like to be engaged with this, please contact me, and I will actually put my email in the chat as well. Thank you.
Thanks, Bill. Okay, we're getting short on time, but we have one more working group, and I am formally the person leading this, but what we decided was that we would, the US group would lead an effort to establish an example of how we would create models of the critical zone. And Doug Miller and Sarah Sharkey have been leading that effort to look at data from the Lamprey River watershed in New Hampshire. So we know that the critical zone, the various sites that we're studying represent a range of Earth's surface environments. And so some of the questions we want to think about are, how alike or different are our various study sites? Where do they fall on a range of land surface characteristics? And where does a potential study location fall with regard to other study sites when we're thinking about the diversity of environmental characteristics? So the approach here is based on a literature in what's called geodiversity, and we're thinking of it as critical zone diversity. And the approach is to overlay and use statistical functions in GIS to create what are called diversity indices for each land surface category, and then sum those to create an overall diversity measure for a study site, being all our partner sites. So far, well, here's just an example of the kind of data we're using from the Lamprey River watershed. And so far, what we've accomplished is we've assembled the land surface data layers, admittedly with some debate on how we're approaching groundwater. It's all been rasterized to a common grid size, and now we just need to determine the diversity of each layer and then the overall diversity. And my impression is, and Sarah, you can comment, but that we should have those done this week. And then once that's done, we'll meet as a full working group, show each of our partners how we did this, talk a little bit about what data they have available, whether we can all do this in a common approach. And then once we've established the common approach, we'll do it across all our study sites. Do you care to comment, Sarah?
No, that's correct.
Okay, well then, let's keep moving along. And I will say that we do not have time for questions, but please, if anyone has any questions for me or for any of the people that just reported on working groups, if you don't remember who the people were or don't have a contact information for them, just reach out to me. I'll put my email address back in the chat, and just reach out to me and I'll direct you to the right people. Now we want to move on to the national presentations.
Hi everyone, welcome to presentation on ABRESO Japan Activity Report 2022. I'm Hideaki Shibata, faculty member of—
Can you raise the volume a little?
The PI of ABRESO Japan here. We have 4 PIs, Yuichi Honda, Osamu Saito, Takashi Gomi, and myself. with 37 project members, including 18 students in various universities and institutes. Here you can see our research sites from north to south in Japan. We have a wide range of climatic and geological settings with different land use management. We will analyze the impact of less forest management and farmland abandonment on soil and water at various research sites, including forest, cropland, paddy field, and wetlands across Japan. Next, we present research highlights in each site.
Research question 1, the drivers is in Japanese team is focusing on the forest management and natural disasters and also deer overgrazing. This is a picture of the forest setting. Various study sites relating to drivers is locating from north to the south of Japan. For analyzing past and future land use change, in particularly the forest, we developing forest database. And we combined prefecture and national data and then using LiDAR airborne analysis and developing detailed forest stand conditions map. Research in the Kyuryu experimental forest conducted by this Masanori Katsuyama is a very unique opportunities for the long-term monitoring of discharge and the water quality change, especially how the forest stand conditions is affected for this water qualities over the time relating to this forest development and forest stand condition change. And he also analyzed how these conditions are affecting for this catchment runoff, with the water qualities, especially in-channel processes, including hyperlic exchange. The research has been conducted for this experimental manipulation and the forest settings in this plantation forest in Japan. And based on this long-term monitoring, how these plantation forests are affecting for this runoff generations and the recovery processes. In these hydrological processes in catchment, bedrock groundwater also be monitored, how bedrock groundwater contributing runoff generation and the formation of this catchment runoff processes. Losing a soil by the landslide is another unique opportunity for looking at how runoff response changing after the landslide in wide areas. And this is an example of the monitorings of this area affected by this landslide and without landslide. Landslide is also affected the catchment scale carbon stocks due to the losing of the soil and the losing of the vegetation. Therefore, this is another good opportunity for this research, how this carbon stock in catchment scale was lost by this landslide and then possibly be recovered after the landslide. In Japan, deer overgrazing is another driver to changing the vegetation types and then inducing a soil erosions. This is an example of the monitoring of this, how this deer affecting and then controlling the population of deer, changing the vegetation recover and soil recovers. Finally, based on this developed data set, which I show you previously, and we also developing evapotranspiration models, applying the various stand conditions and the various rain and snow characteristics, and then estimating wide area of this evapotranspiration, including transpirations, interception loss, and the forest undergrowth evapotranspirations.
I'm Yu Chonda, University of Tsukuba, and PI of RQ2 and line mechanics. We studied land abandonment by Fukushima nuclear power plant and their recovery in Nida River catchment in Fukushima, Japan. So in 2011, nuclear power plant accident occurred and then the people evacuated. So the land is abandoned. And after that, the government decided to decontaminate the agricultural land to replace the surface soil to the deeper part of the soil. So we analyzed the land abandonment and recovery by using the remote sensing technique. And we created fusion image of Sentinel and Landsat and draw a NDVI map during summer. So then we found that NDVI is lower 2050 to 2070 in most of the places and recovered in 2018. And then we converted this to erosion potential, and erosion potential is higher during the same period. We correlated the soil loss and the suspended sediment load, and also erosion potential to suspended sediment load, and we have a good correlation so that the sediment to the stream is coming from the mostly the decontamination pit land. Also, we can use the cesium as the tracer of sediment sources. This graph showing the temporal change of cesium concentration from the Nida River. So as you can see, the cesium concentration decreasing during the decontamination period and then return to the similar tendency. We use this data as the sediment source determination. So during the decontamination period, the sediment is from 80% of the decontamination land to the downstream, but recovered pretty quickly. This result has been published in Nature Sustainability this year, and our findings demonstrate that upstream decontamination causes persistently excessive suspended sediment load downstream, though with reduced cesium concentration, and that rapid vegetation recovery can shorten the duration of such sustainable impact. Also, my colleagues have been studying environmental recovery after Fukushima accident in forests by measuring the downward migration of reduced cesium, and also studying the environmental recovery of cropland and paddy field. Our students have been doing intensively their work, and they will explain their activities.
I'm Discharge, second year master's student at the University of Haupt. I'm observing tributary river and headstream in the Fukushima prefecture. I observe water level, stability, and cesium concentration of suspended sediment to investigate the environment impact of decontamination. Thank you.
My name is Shunsuke Nishima. I am an undergraduate student at the University of Tsukuba. I investigate the effect of prefinancial flow on downward transfer of radiosity. I conducted artificial rainfall experiment using the tracer last week. I want to know the difference of radioactive concentration between stent and non-stent soils. Bye.
Hello, my name is Joy Takamura. I am undergraduate student at the University of Tsukuba. I am conducting research to quantify the effect of singing using the geophysical openness as an indicator. I mainly calculate the degree of openness from survey point cloud Currently, I use a ground laser to service data. This is a laser called by all system. We can survey forest data in this way.
So next report is from northernmost of Japan. The Bekanbushi River watershed is located here. And this watershed is connected to the Brackish Lake and coastal area. The watershed is covered by forest and farmland. This is the daily pasture land. And you can see that wide range of riparian wetland from middle to lower part of the watershed. So this river is affected by tidal fluctuations because of very close to the oceans. So we developed some observation sites and observed the hydrological and biogeochemical processes and try to understand the effect of tidal fluctuations on river water flow and solute concentrations such as nitrate and DOC concentrations. We had intensive hydrological and biogeochemical observations at this Bekanbushi River watershed. We observed temporal change of river water and solute concentration, including the tidal ebb and flood. Nitrate and these DOC concentrations were observed using high time resolution in situ sensors with 10 minutes intervals. And we are trying to understand the CQ concentration and discharge relationships under the tidal impact of this lower watershed. These are some results observed this June, and left two figures show the temporal change of nitrate and DOC concentrations this June. So red colors means downward river water flow, while the blue colors means the river's upward water flow. You can see that nitrate and DOC concentrations are largely fluctuated with directions of water flow. And then three light figures shows the CQ plots for nitrate, river volume transport, and nitrate concentrations. These are same plot, and again, red colors mean downward, and blue colors mean upward. And the size of the plot represents the DOC concentrations or EC electric conductivity or water temperature. So you can see that the slope of the CQ relations is different between the downward and upward water flow affected by tide. And then CQ relationships is often disturbed by the high EC data, that means mixing of seawater, and also the low water temperature affected by the rainstorm. So these results suggest that tidal fluctuations strongly impact on the hydrological processes, also the formation of concentration, nitrate and DOC concentration in this lower watershed. And then this watershed, Bekanbushi watershed, is used for our student exchange program between US and Japan. So we invited US PhD students, Eric Parker, who is working on hydrology and biogeochemistry at the Lamprey River Hydrological Observatory in New Hampshire, United States. Eric and we worked together in the Beckham-based watershed for his intensive collections of samples, river water samples, in tributaries and many channels in this watershed. So we are so excited to see his comparable analysis between US and Japan in his AGU presentation this December. And also we are excited to our further progress of country-to-country collaborations under the ABRESO project.
Hi, my name is Osamu Saito from the Institute of Global Environmental Strategies, IGES. I'd like to give you a very brief overview of the case study at the Beckham-Bush River watershed located in the northern part of Japan. And this watershed size is 749 square kilometers, which belong to two municipalities, Akeshi Town and Charlestown. And total population is around 6,000. This table on the right shows the result of the previous workshop. We discussed about who are the stakeholders, what are the major land use changes, what are the drivers, and what's the major ecosystem services and disturbances, and what kind of land management policies are discussed or implemented. In terms of stakeholders, fishery, the dairy farmers, major the stakeholders, and in terms of the drivers, depopulation and aging is a serious problem. And then I see one of the policy instruments identifies payment for ecosystem services. After my presentation, Dr. Haga from Osaka University will further explain about the case study. And after that, Dr. Arno from Taiwan will explain about the Japan-Taiwan collaborative research. Thank you very much.
Thank you for the introduction. I'm Chihiro Haga from Osaka University, Japan. I'm a postdoc researcher. Our case study site is the Beckham-Bushi River watershed in northeastern Japan. Most of the watershed is covered by forest, and the remaining 20% is covered by pasture land for dairy farming. So aquaculture, dairy farming, and forestry are the main industries in this site. In this site, depopulation is a critical driver of landscape change. By 2050, the population will be decreased to the half of the current level. The expansion of red grid cells shows how this is a severe problem. So we have simulated future landscape change scenarios using the landscape change simulator. So first, we have used the result of questionnaire survey to stakeholders to set up our scenarios. And then the model computes the vegetation change for each grid cell, considering climate change and management activities. Then we have evaluated the future biodiversity, ecosystem services, and expected renewable energies. And here are the results of our simulation. Due to the time limitation, I can't explain everything today, but we have successfully simulated future land use, timber and pasture use, carbon sequestration, biodiversity, and renewable energy nexus. In brief, our results suggested that stakeholders' preference for natural resource use is a key to changing the local critical zones structure and services derived from them, even in a shrinking society. And we are trying to evaluate land-ocean connectivity by collaborating with the Hydrologic modeling team. Our future land use and land cover dataset are shared with the team, and they are now setting up the simulation.
Hello everyone, I'm John. I'm from Taiwan. Today I would like to talk about the Wymore project, collaborative research between Japan and Taiwan. The picture shows evaluating interaction between water system and socio-environmental dynamics. In Taiwan, I focus the gap between governing institutions and local stakeholders performance in the watershed socio-ecological system. You can find the resource one. We need a better social fit between governance, and local stakeholders in Pinyin. And based on this research, we extend our discussion of another study. We hope to provide another suggestion using the concept of payment for ecosystem servers to build small wastewater treatment plants and water supply infrastructure for the local area. We design 4 different scenarios by water evaluation and planning. Now, the research is still ongoing. Finally, when we finish, we will write a journal article. This is my visit to the Fukushima study site and conference in Japan. Thank you for your listening.
This summer, Japanese group has been visited to the United States and learn a lot of things. I hope all the members will come to Japan and see many different things and hope to compare different settings of dam degradation and their recovery. We visited University of New Hampshire to see critical zone site and Harvard Brook LTER site. We thank you very much to host our visit. I invite Bill and Adam to introduce the critical zone site and a lot of monitoring points. There are also guiding very famous Harvard Brook site. That visit gives us a very good idea of the geographical setting and the water and their results. And some of our colleagues also visit to Clear Creek watershed and see many different scenery and the soil profiles. My colleague loves this profile very much. So hope next year, please visit Japan and maybe 4 or 5 day tour will be possible to visit, such as Hokkaido site, earthquake-induced landslide and their recovery, and Fukushima site, decontamination, and Karasawayama site to see the forest recovery, and then Paddyfield site in Okayama or Kiryu or anywhere in Japanese site. Anyway, we welcome very much for the possible visit next year and discussing at the field site, hopefully next year. Thank you very much.
Good morning, good evening, everyone. This is Bill McDowell. I'm lead on the U.S. portion of the ABRESO project. We will cover today both the natural science and social science aspects. What we'd like to do today is go quickly over how we're looking at the relationships between land use, land abandonment, land use change, and water quality. And presenting for natural science will be myself, Adam Wymore, Denny Murray, Eric Parker, and Hannah Fazekas. We have a lot of ongoing work that is the backbone of ABRESO and provides some of the context that we use. We have long-term sampling of water quality across land uses. We have sensors that document short-term variability in water quality. We compare our sites with other sites, and we try to understand how river quality is linked, water quality is linked to Great Bay, and the implications that has for environmental management. And I highlight here the eelgrass resilience project that is ongoing and is run out of UNH. I'd like to speak to one new project very briefly. This is a National Science Foundation funded project that looks at how urban transformation affects greenhouse gas production by inland rivers and ponds, specifically looking at comparisons between the built and the natural environment. Component of this is a comparison between the Lambert River Basin and Beijing City, China, and we'll specifically look at the carbon dioxide, methane, and nitrous oxide production by these inland waters across the rural-urban continuum. Thank you, and now we'll turn it over to our next speakers.
Hi, my name is Eric Parker, and I'm here to talk to you about Sister Streams, a collaborative effort between the University of New Hampshire in the United States and Hokkaido University in Japan. The exciting thing about Sister Streams is that it represents a unique opportunity to treat two of our study watersheds as natural replicates due to their similarities. They are both characterized by similar land use, land cover, annual discharge, watershed area, climate, and terminate in economically important estuaries that are threatened by nutrient pollution. To do this comparison, we selected 16 sites at each watershed, 8 main stem and 8 tributary. Our sampling protocol involved a spatial component and a temporal component. Our spatial component involved going to each of the 16 sites every day for a week, and our temporal component involved collecting 2 12-hour time series at one of the lowest points in the reach to integrate the impact of a rain event throughout the watershed. We're now moving on to the point where we're analyzing all of our samples and very excited to see exactly what type of comparisons we'll be able to draw and find out exactly what type of sisters they are. Thank you.
The Lambert River Hydrological Observatory has been measuring wet deposition chemistry at a weekly, year-round scale for nearly 20 years. This deposition gauge is located near the most downstream mainstem river monitoring location, which is also monitored on a weekly basis for a similar time period. The map at the top of the page is of the Lambert River watershed, with the deposition site marked with an X and the river site marked with a red dot. And below are 2 photos of the sampling locations, so you can get an idea of the type of river system that we work in. These 2 datasets provide over 1,000 spatially and temporally paired observations of precipitation and discharge, as well as organic nitrogen and inorganic nitrogen species, which are shown in the normal and the week of year scatter plots on the left side of the page. These time series datasets provide a unique opportunity to explore the synchrony between deposition nitrogen and river nitrogen concentrations. We quantified synchrony between organic and inorganic nitrogen inputs and outputs using information theory. Information theory is a probability-based metric for assessing the reduction of uncertainty that deposition time series can provide to river time series. If deposition can reduce the uncertainty in river time series, then they display some amount of synchrony at a predetermined lag time. We calculated 2 metrics, mutual information and transfer entropy, to show the amount of information transferred between deposition and river that follow likely transformations within the nitrogen cycle. So, for example, ammonium inputs via deposition and nitrate exports via the river would equal nitrification, while organic nitrogen inputs via deposition and ammonium exports via the river would equal mineralization. Information transfer was quantified across lag times from 0 to 26 weeks, as shown on this example plot on the right side of the page. So, for example, we asked how much uncertainty is reduced at week 0 compared to week 20. And the timing and magnitude of maximum uncertainty reduction is when the influence of deposition time series on river time series is the greatest, which is circled on this plot. We found that deposition nitrogen time series can reduce uncertainty in river time series by a maximum of 45% at lags of 15 to 17 weeks when just considering the full data record. This can be seen on the leftmost cord diagram, where the width of the cord can be interpreted as the magnitude of information transfer from deposition to river. So for example, if you follow that hot pink cord, the DON deposition influences nitrate river concentrations, leading to 45% reductions in uncertainty in the river time series. We performed this same analysis for dormant and growing seasons as the study watershed displayed distinct phenology. And we can see that information transfer magnitude is higher when considering seasonal data, which is displayed by the much larger cord widths, but there are fewer types of biogeochemical synchronies present. Because mutual information and transfer entropy are causally based methods, we can then form a conceptual model on the fate of nitrogen deposition in a watershed. For example, ammonium deposition is assimilated or nitrified within the terrestrial or river environment to show up as nitrate or DOC in the river 15 to 17 weeks later. This lag time is indicative of both transport and transformation time that nitrogen and water undergo in the watershed. By summarizing data from deposition lag to river time series at maximum uncertainty reduction, which is shown in the scatter plots on the page, we can also see that as deposition concentrations increase, the biogeochemical pathways that convert inorganic to organic nitrogen can saturate, shown in these plots with breakpoints at about the 0.2 milligrams N per liter. These types of causally driven conceptual models provide a nice set of hypotheses to test using experimental approaches in the future.
I will be presenting the social science data we have collected in New Hampshire, located in the northwest part of the United States. We began our research by determining salient issues related to land use change in the New Hampshire study site area and identifying proposed policies to address the issues. We selected water quality as the issue most likely to resonate with the residents in the area. We selected 10 policies that ranged in how comprehensively they addressed water quality and their political feasibility. Our first survey of residents in the area explored perceptions of the Lamprey River and support for policies that would protect the water quality in the river and beyond. Rosemary Avista will summarize findings from this research.
One of the projects we worked on this past spring involved surveying residents in the Lamprey River watershed area of New Hampshire about their perceptions of water and water policies. The survey came about as a collaboration between the Lamprey River Watershed Association and researchers from the ABRESO project. The Lamprey River watershed is one of the major watersheds feeding into the Great Bay. Therefore, the health of the river and its tributaries is important not just for the watershed's health, but also for the health of the bay. Currently, the Lamprey River is classified as a Class B river, which means the water quality is generally okay, but it still needs to be maintained. The purpose of this specific survey was to understand residents' perceptions of the Lamprey River and their specific concerns about the health of the river. We were also interested in resident support for water policies and factors leading to that support. For the survey, we recruited just over 1,000 participants from the Lamprey River watershed area and received back 194 responses. And then after exclusions, we had a final sample of 168 respondents. Respondents were all from 2 counties in southeast New Hampshire, and more than half of the respondents live on the banks of the Lamprey River or one of its tributaries, and the other half live on average about 1.5 miles from the river or one of its tributaries. In the survey, we asked information on a range of topics relating to the Lamprey River. First, we were interested in residents' perception of the river's water quality and how engaging in activities on the river impacted these perceptions. We also looked at people's concern about different conditions of the river and their perceived threats to the health of the river. Then we asked about resident support for different policies addressing water issues and how perception of water quality, concern, and perceived threats impacted their policy support. And finally, we looked at how connectedness to place, such as one's town, the river, the Great Bay, and nature more broadly, impacted all of these variables. So we found that on average, participants believe that water quality is good and that these perceptions were informed by visual observations of the water. Also, that engaging in activities on the river is not associated with their perceived water quality. When looking at 2 types of concern about the water, respondents were more concerned about pressures on the river, such as pollution, than states of the river, such as erosion. Looking at types of perceived threats, respondents perceived non-point sources of pollution to be more threatening than point source pollution or climate change. And then looking at policy support, respondents reported the greatest support for policies that maintain and restore the natural environment, such as purchasing land for conservation, more so than the other types of policies. Looking at what is associated with policy support, all types of concern and perceived threat were associated with greater policy support, although perceptions of water quality were not. And respondents concerned about pressures on the river was associated with policy support over and above concern about states. And finally, respondents' perceived threat of point source pollution and climate change were associated with policy support over and above perceived threat of non-point source pollution. Finally, with a few exceptions, feeling connected to some part of nature was positively associated with all variables, but unrelated to perceptions of water quality. However, feeling connected to one's town was not associated with any of the variables. So just to recap, residents were connected to and engaged with the area and generally perceived the water quality to be good. However, they're also concerned about the river, perceived threats to the river, and support water policy. The extent to which they're connected to some part of nature, are concerned about the river, and perceived threats to the river, the more they support policies addressing water issues.
A second survey in the New Hampshire region tests perceptions of and support for 3 water quality policies. We selected 3 policies from the 10 that we included in the Lamprey River Association survey. We selected them to represent 3 general types of policies that Rosemary noted. We needed fewer policies because the type and number of questions we wanted to ask respondents was extensive. We did not provide any information about the outcomes of the policies because we wanted to know residents' default unprompted expectations. We finished collecting the data from about 400 residents living in our New Hampshire study site. There are 2 types of analysis we plan to do with the data. The first is text analyses of respondents' descriptions of the 3 most positive outcomes they anticipate from each policy and the 3 most negative outcomes they anticipate from each policy. Joe Guerrero described analyses we will be doing with this data.
Hi, everybody. My name is Joe Guerrero, and I'll be discussing how we plan to explore and understand what kinds of things people are thinking about when they're asked about different water quality policies. Because we have thousands of open-ended responses, the way we're going to explore this is with a machine learning approach known as topic modeling. Topic modeling is an unsupervised machine learning method used for identifying themes or topics in a collection of written text. And written text could be anything from tweets to books to, in our case, open-ended responses to survey items. The specific topic modeling approach we're going to be using is known as latent Dirichlet allocation. In a nutshell, this is how the process works with a simplified example specific to our application. We start with a collection of text documents, or in our case, a collection of open-ended responses to a question. What we then do is we take every unique word used across all of the documents, of which I've only shown a subset here in the table, and we put these words into a matrix. Then for each document, or each person's open-ended response, we count the number of times each one of the words was used within their response. Now that we have a matrix with this count data in it, we can essentially do a cluster type analysis to find the most prominent topics. Our output gives us 2 pieces of information. The first piece, or pieces of information, are lists of the most common words associated with each topic. In this example, we specified that we want to look for 2 topics. These lists of words help us label the topics and assign meaning to them. The second piece of information that we get is a percentage score for how well each topic represents each document or open-ended response. This piece of information will allow us to estimate the relationship between the topics that participants had in mind and any outcome variable of interest, for example, policy support. With topic modeling, we'll be able to explore our open-ended data in a variety of ways. For example, although we started with considering each open-ended response per each respondent, as seen here, we can change the frame of reference. By doing this, we can understand how topics differ not as a function of who the respondents are, but what questions are being asked. Maybe there are topics that are unique to responses to questions about benefits versus consequences of water quality policies. Additionally, we'll explore differing number of topics that we consider. As always, in a cluster analysis, the number of clusters considered are specified by the researcher, and we'll be exploring topics that emerge under different clusters or K specifications. Ultimately, we're going to be using machine learning to identify and explore themes and what people are thinking about when they're asked about water quality policies. We're going to explore themes that emerge when participants are asked about policy benefits versus consequences. And we're going to test how these common themes relate to policy support. Thank you.
Respondents also completed other measures that we anticipate will be associated with their support for and preferences among the three policies. For example, they rated the extent to which they thought the three most positive and negative outcomes of the policies were good to bad. Then they rated the likelihood that the outcomes would emerge. The perceived value times the estimated probability the outcomes would emerge are predicted to motivate support for the policies. We also assess their emotional reactions to each policy. Emotions are important because they represent summative assessments of policies, suggesting reasons why they like or dislike policies. And the emotions are motivational and thus should also predict support for policies. Our research in other US samples suggests that the more worried, angry, and neutral people feel about policies, the less they would support them. This research also suggests that the more hopeful they feel, the more they will support the policies. Among these emotions, hope is the strongest predictor of policy support. This suggests that people's feelings of the effectiveness of the policies is the most important reason why they prefer some policies more than others. The next survey we will conduct will test whether different types of information alter the policy support by, for example, changing expected outcomes or emotions about the policies. Another question we have is whether other stakeholders have different perceptions of the policies. Thank you for your attention. We look forward to your questions.
Thank you to the US team for that presentation. We have a couple minutes left if anyone has any questions.
Well, I'll ask a question if no one else has one, which Janet, you raised the issue in one of our last management committee meetings of how the social sciences efforts are informing the natural sciences and vice versa. And I'm just curious to know what your thoughts are on that. And I'll just add that my impression is that we're not really doing that yet. And so I guess an additional question would be, how can we?
That's the conversation of the of an hour or so probably. But no, I think some of the ways that the natural sciences has helped us in terms of actually part of it is understanding why policies are important. And so the natural processes that occur from human behaviors that then affect the carbon concentration or with the water quality. So and I think it's affected the sorts of policies we pick to study. So the ones that should be the most effective. And one thing that's not mentioned here is that when I say giving people information, we have found in some state data that if we tell people how a policy matters, so that the soil filters the water, and that's why concentration discharge is important and it needs to be filtered through. And so the importance of different concepts, so the importance of different concepts like concentration discharge is something that was mentioned, but I had to learn what that was to even know why that was important. So I think that's informing the policies we pick, and then eventually what we would think are important for people to study. I don't know how the social sciences are informing the natural sciences. I have the same sort of impression that they're separate. And I guess that's a start. I guess it will also be in terms of eventually when we think about what are the things that the open-ended data, for instance, that Joe was looking at. So what is it that people are talking about when they talk about water quality, and how do they align or misalign with what the natural scientists are talking about?
Thank you. But it seems to me like that might be something we want to discuss more, maybe including in our breakouts on day 3 or at another time. I think it's a good topic of discussion. Anyone else have any questions or comments? All right, well then I'll remind you that we'll pick up again on Monday, a week from today at 7 a.m. for presentations from our French, Italian, and Taiwanese colleagues. And then day 3 will be where we break out and have some conversations on Wednesday, November 16th. So thank you for your participation. And for those of you leading the generation of presentations for next Monday, please get them to us by Thursday. Thank you.
Thank you, everyone.
Bye.
Thank you. Bye.
Thank you.
Bye-bye.
Thank you.
Thank you.
Bye bye.
Bye-bye. Gli do 1, 2, 3.